This Cure application achieves monitoring the urban heat storage using cross-cutting information from the Copernicus services. Observations of global temperature evolution indicate a pronounced air temperature warming, since an increase in the occurrence of heat waves and the urban heat island effects tend to exacerbate such warming. Among all the effects caused by the substitution of natural ecosystems for urban land use, the most pronounced is the increase in the amount of energy stored in the urban canopy, especially in buildings and paved surfaces, which is approximately 2 to 6 times larger than in non-urban canopies. The slow release of this energy stored in buildings and paved surfaces in cities causes the urban heat island effect, and it is related to the energy efficiency and consumption in cities. The heat storage is defined as the net flow of heat stored within a volume that includes air, trees, buildings, and ground. The ability to absorb, store, and release heat depends on the thermal mass and the morphology. More details on the urban energy balance and the various urban heat fluxes are explained in the Urban Heat Emissions Monitoring application presentation. This application provides time series maps at local scale, that is 100-meter spatial resolution, of the heat storage flux at the time of Sentinel-3 acquisition and operates for the cities of Heraklion and Basel within Cure. This is an illustration in the right-hand side of the heat storage change during the day for different materials in an area in London. On the left-hand side, you see the surface temperature variations for different urban surfaces from sunrise to midday from installed thermal cameras in the Barbican area. We can observe different behavior in terms of heat storage for the different urban surfaces. For example, the roof and wall surfaces, illustrated in this graph with yellow and purple lines respectively, start storing heat almost immediately after the sunrise. This is not the case for the street surfaces, with a red line in the graph, which start storing heat later but much faster. Choosing the right materials and paying attention to the orientation of the urban surfaces is obviously important when planning, and tools like this can quantify the heat storage at local scale, allowing identification of possibly problematic areas. This Cure application is using the so-called objective hysteresis model, OHM, to quantify the urban heat storage. The hysteresis effect on urban flux storage indicates how quickly the urban surface responds to the input of energy and its association with the diurnal evolution of the boundary layer, varying according to the characteristics of the area. Detailed surface information, along with air temperature and surface temperature information, is used with the OHM to achieve the spatial representation of the urban heat storage. Various sources of data from the Copernicus services and satellites are used to achieve this. You can see here an example of heat storage maps for the city of Heraklion. Cure provides heat storage flux maps for the Sentinel-3 acquisition times, that is twice per day, because of its dependence on the surface temperature products. The map values represent the rate of energy exchange between the atmosphere and the surface, with positive values indicating energy storage in urban surfaces and negative values indicating energy release. In the daytime map, at this time of day, long after the sunrise, all areas in Heraklion store energy at different pace, while in this nighttime map, all areas release energy at a different pace. Bare surfaces, such as the rocky hill in the northeast part of the city, as well as the core of the city, store energy in a much faster rate than the surrounding, mostly agricultural and vegetated surfaces. While surface heat storage maps like these can directly provide quantitative information on the rate of heat storage and release for different urban surfaces, in order to have a comprehensive overview of the city's heat load, we need the combination of all heat-related applications. Only these can provide complete information on the heat load for different times of day and different seasons, including past and future, for monitoring reasons, but most importantly for supporting mitigation and adaptation strategies to reduce heat.